Hello to all our virtual viewers. This is MFPS 36 2020. This year we are having the conference online, virtually. What are partial evaluations? So if you don't know what a monad is, here's the definition, but let's try to give it a more practical and operational interpretation. So the idea is that let's work in the category of sets. A monad is like a way to form formal expressions consistently. What I mean is that we can consider our sets as containing just some variables or elements. And then a monad has a functor, first of all, that takes a set and gives a new set which contains formal expressions in these variables. For example, formal sums. So in this sense, formal sums, what does it mean formal? It means that this sum somehow does not see the content of this variable. So maybe it's helpful to wrap the variable inside a box to say that this plus does not have access to the inside of the box. Okay, so this is a purely formal sum. x1 and x2 don't have to be numbers. They can be literally those letters. We can still sum them formally, right? So we can take binary sums, ternary sums, well, singleton sums, sum just this thing to nothing, or even the empty sum, okay, and so on. Of course, not just sums, this is more general. Sums are an example. Now the functor is an endofunctor, so it returns a set of these expressions so we can iterate it. And we get formal expressions of formal expressions, namely nested formal expressions. So with two levels of boxing. So you see the plus in here has no access to the inside of this large box, but the plus in here does. It just doesn't have access to the innermost level. And on functions, so on morphisms, well, you apply the function box-wise or element-wise. So if you have x1 plus x2, then tf just applies f inside each box. Okay? Okay, that's the functor part. So we also have a unit. So a unit is a way to take an element of x and just give a formal expression. In our picture, we can wrap this element around its own little box. And there is the multiplication, which takes formal expressions of formal expressions and flattens them to just formal expressions. So in our picture, we can just imagine that this removes the outer boxes, okay? And in particular, it equates the level of this plus and this other plus. What do the diagrams of the monad mean? So the first unit diagram says that if we have a formal expression and we wrap it inside a box, so we make this double formal expression, which is rather trivial. It's not really double, so to say. And you remove the outer box, and you get back to what you had before. The right unitality tells you that if you again start with a formal expression and now apply eta element-wise. So inside each box, you put these elements in their own little boxes. Again, so now the inner level is kind of trivial, right? And if you remove the outer boxes, you get, again, the initial expression. The multiplication or associativity square says that if you have now a nested formal expression, so 3 levels of boxes, and you can do either you remove the outermost box, apply mu, or you remove the mid-level boxes, which is inside each box, here there's only one, you remove the boxes, so these mid-level ones. You get doubly formal expressions here, but different ones. If you now apply mu again, you get the same thing, and the reason is because you're basically removing the level that you didn't remove before. So only the innermost level remains. Okay? So this diagram commutes. So the diagrams of the monad can tell us that this interpretation is consistent, so that you can interpret monads in terms of adding and removing boxes in your formal expressions. Okay. Now, all of these were formal, but of course we have some places where we can actually do sums, like numbers. So if you have 2 plus 1, of course it's formal just like x plus y, but 2 plus 1 is equal to 3, right? So we can, in some cases, remove the boxes, and now the plus can, if you want, access these variables and operate on them. So whenever we can do that, we speak about an algebra. An algebra is a place, if you want, a structure where these formal expressions with these specified types of formal expressions can be evaluated to an actual result. Here's a more rigorous definition. So it's first of all an object of your category, for us a set, and the map from formal expressions to our set, which takes the result, which have to be consistent in the following sense. First of all, so remember we have the unit, the given an element just gets a kind of trivial formal expressions that just contains that element. If you evaluate that, then you need to get that element back. So that's a unit triangle of the algebra. The other consistency condition is that if you have a nested formal expression, then again you can do two things. You can either flatten it, removing the outer boxes, and somehow integrate these two levels of sums into just one larger sum, or you can remove the inner boxes and so evaluate the stuff that's in here. So you get two formal expressions that on the nose are different, but if you evaluate them, if you evaluate those things, you get some kind of total evaluation, and these two ways coincide. All right? So in some way, it tells you that evaluating a formal expression that comes from mu is the same thing as a double evaluation. So mu kind of packs this double instruction together into a formal expression that contains both steps. All right? So that's an algebra over our monad. Many algebraic structures, almost all of them, can be modeled as algebras of a suitable monad, either on set or on other categories. So it's actually a very powerful construction, you probably know. Pretty much every monad can be interpreted, at least on set, as formal expressions, as long as you allow for potentially infinite formal expressions. Okay? So now, so far, we could evaluate things totally all the time. But one may ask, okay, how about partial evaluations? So there are some situations, I will give some examples in a moment, where one is interested in something that looks a bit like this. So you have a sum, and you don't evaluate it completely, but just partially. So maybe in computer science, when you have, for example, an array of numbers that you want to sum, and you want to fold it, but you're not done yet. That's the kind of stuff that you get. But this is more general. Like, this models some very different situations, not just this one, okay? How do you even talk about this in terms of monads, the way we have talked about it so far? Since we know there's box schemes of adding and removing boxes, the idea is that we first want to do this part of the expression. So we first want to sum 2 and 3 and leave 4 for later on. Or, in other words, there is a nested formal expressions. It first groups 2 and 3. And now, we can of course flatten it and remove this grouping and get our initial expression. Or, we can remove the inner boxes this time. And so the large box will now be the one that contains a 5 because we have removed the inner boxes and operated the sum. The rest will stay as it is. Okay? Now we know what these maps are. The map that removes the outer boxes is the multiplication, and the map that removes the inner boxes is, well, inside these boxes, you evaluate. Okay? So here's our definition. If you have P, Q, and TA, then for some mu and TTA, mu of M gives P, and TE of M gives Q. Okay? So whenever this happens, we call Q a partial evaluation of P, and P a partial decomposition of Q. You see, this is also a way to decompose further this expression. Partially. Sometimes we will refer to M as the partial evaluation, or as the witness of partial evaluation, because you can consider this nested formal expression as the instruction to partially evaluate this into this, or decompose this into this. Okay? Depending on whether we want to consider this as a structure or as a property. So both ways are actually helpful. All right. Here are some further examples. So if you take the free semigroup monad, so algebras are semigroups, and as an algebra you take natural numbers with multiplication excluding 0 and 1. Okay, so the unit is not there, but it's okay because we just want semigroups. Then the partial decompositions are factorizations. And there's a total decomposition, that's the decomposition into prime factors. So take a number. There's many ways to partially decompose this. Okay? But actually, all these ways have a common refinement that's going to be the total decomposition. And here is why we're excluding 1, because if we hadn't excluded 1, then you could go further as much as you want by just adding ones. I mean, multiplying by 1 as many times as you want. Technically, it's a different formal expression. We don't want that, okay? Partial decompositions are to total decompositions as factorizations are to factorizations into primes, where you cannot go further. Here's another one. So you probably know that if you have an internal monoid or an internal group in any monadal category or Cartesian monadal category, if you don't know what these are, just imagine sets and the group or monoid object, like a group or a monoid. Then multiplying or tensoring with G gives a monad. This is sometimes called the action monad, or in computer science this is called the writer monad, where this is a monoid usually given by some strings that can concatenate. If you're not familiar with this construction, you can look on the NLab. There's an article that explains this in pretty accessible terms, I would say. So now the algebras are the G spaces, or spaces that have an action of this group or monoid. Okay? So now, what do partial evaluations look here? We can plug in the definition. So first of all, TA here is G times A. So formal expressions are pairs with an element of A and an element of G, which you can think of as a formal action, like a formal translation. A way to think about this is like if A is a set of places and G is the amount of gas you have to reach a certain place, then X is where you start, and G is how much gas you have in your car. Okay, but you still haven't gone to your destination. It's still there. It's somehow still a potential move that you can make. Okay. Now, plugging in a partial evaluation from this to this, if it exists, is an element of TTA, so G times A, such that HL is G and LX is Y. So this looks a bit abstract. What it means is G, so this amount of gas, is actually this amount of gas together with this amount of gas. So let's partition our gas tank. And now, just use the L part to move. So if this would be all that you can move using G, what's a partial translation or a partial action is, so if G is a composition of L and H, you just move off L, not of H. And instead of going all the way, you just go, halfway or somewhere in between. All right? Now, if you think of G as a group, this is rather trivial because you can always do this along an orbit. Just, multiply by H to the minus 1. On the other hand, if we have monoids, so if this is really gas that you consume and you can't get it back, then this is a non-trivial thing. You're going some way in the direction of the orbit, usually you can't go back, and you're, just going halfway or just a little bit along that direction, not completely. So again, it's a partial move. All right. Something that you probably wonder by now is, if I have a partial evaluation and then I do again a partial evaluation, the composition is again a partial evaluation, right? Actually, not always, but sometimes it does. So for the nice cases, we do have that. So for example, for the case of sums, so suppose you can partially evaluate this into this, well, using this witness, and this into this, using this witness. Now, do we get a partial evaluation witness from this expression to this expression? And I don't mean in 2 steps, I mean in a single step. So the idea is that, okay, look, here, this 2 that appears also here was obtained by doing 1 plus 1. And this one, just the same. Okay, so let's replace this 2 in this expression with the way it was obtained. So now you have a triply formal expression, so doubly nested. And what we can do is now somehow pack the instruction by removing the innermost arrow. So removing this division, because we want to do a single step. That's the instruction that witnesses a partial evaluation from here to here. You see, removing the outer boxes gives this, removing the inner boxes gives this. Okay? So for the listeners which are familiar with operads, this may ring a bell because we are substituting something in here, so that may remind of the multiplication of operads. That's kind of the case. I'll get to that in a moment. So the thing is, we want these expressions to exist. These triply formal expressions that can be interpreted as in substituting this into this. In other words, we want this property. So if there's something in here and something in here such that they agree down here, then there needs to exist an element up here that closes the diagram. Okay? Almost like a pullback without uniqueness. So what is this thing that's kind of like a pullback but not quite? It's called a weak pullback or meek pullback sometimes. So the idea is that you have a square and you have elements here and here that agree down here. We call this a weak pullback if when this is the case, there is always an element in A, such that gets mapped to C by G and to B by F. It's a pullback without uniqueness. Now, you probably know that a Cartesian monad is a monad that preserves pullbacks, like the functor preserves pullbacks, and the neutrality squares of either mu or pullbacks. So just as well, one can define a weakly Cartesian monad is the same, but T has to preserve weak pullbacks, and the neutrality squares are weak pullbacks. Now, for weakly Cartesian monads, composition is always defined, because we can always fill up the square before it was marked in red. And for Cartesian monad, it's even uniquely defined, because there's a unique rewrite or free writes. Okay, when are monads weakly Cartesian? So, well, all monads presented by an operette are Cartesian. So there, this composition of partial evaluations is really a substitution. It's really the operatic operation on the nose without any additional identification. So by operette here, I mean plain operette. I don't mean symmetric operette, okay? So those things are like equal on the nose, not even up to permutation. This includes monoids and group actions. No, not monoids and groups. Monoid and group actions. Okay, so this tensoring with a group object, for example. Many monads are weakly Cartesians. For example, the free commutative monoid monads. So roughly, if it's presented, like if it's finitary and presented by a symmetric operas, then you get weakly Cartesian, and the uniqueness fails because of permutations. The generic monad is not weakly Cartesian. Okay. The case that interests me the most, since I work in probability theory, is probability monads, in particular the Kantarovich monad and the distribution monad on sets. For those, composition is weakly Cartesian. Unit is not, but we don't care. We want composition to compose partial evaluations. Okay, let's talk for a little bit about probability monads. We've seen that monads can be seen as constructions encoding formal expressions. So in probability theory, you sometimes are interested in taking formal convex combinations or formal averages. You have a base category, could be sets, metric spaces, measurable spaces, whose objects you can think of as being spaces of possible states, in general deterministic states. For example, the space X, which you can think of a coin, has two states, heads and tails. Now, the functor takes a space and gives you a new space of the, so to say, random states, like formal convex combinations of these elements. For example, it contains half and half, heads and tails, with like 50-50 probability, or 100 and 0, 75, 25, and so on. Now it's important that these are formal averages, okay? You're not actually taking the average of heads and tails. There's nothing in between. The coin does not like land vertically or something. This is not some kind of superposition of states like in quantum mechanics or some kind of real average, right? It's important that a probability measure is a formal average. You haven't taken that actual midpoint or center of mass, right? Formal. That's why monads are so useful here. Now, clearly, a completely deterministic state, like 100% coin, 100% heads, correspond to just heads. So there's a natural map from X to Px that picks out somehow the deterministic states in there. That's the unit of the monad. And more interestingly, suppose that I have a fair coin in my pocket. It could be heads or tails. And this loaded coin in my pocket that's like has two heads. Okay? Now, suppose that I have both coins in my pocket, and I draw one of them at random and then flip it. You've probably done that in your head. The total probability is that I'm going to have like 3/4 heads and 1/4 tails as outcomes, right? So think of what this was. Also, the coin is random, like which coin I pick. So that's like a random coin, like a random outcome, right? This was actually an element of PPX. We have a law on the random variables as well, like a law on the laws. And by kind of averaging out, we get a normal random variable, okay? That's the multiplication. So this kind of averaging, again, formal averaging, that's the multiplication, okay? So what are the algebras? Well, the algebras are where you can actually take those averages. So convex spaces of some kind. If you have, probability measures over these 2 points, then you can map a probability measure. So this 100% of A goes to A, 100% of B goes to B, and stuff in between will go somewhere that, if you want, like physically in between. It's a kind of midpoint or like convex combination, right? So the spaces where you can do this are convex spaces in some sense. So if you do this for the distribution monad on set, you get what are actually called abstract convex spaces. If you do this on metric spaces, you get convex regions of Banach spaces, and so on. So depending on the context, depending on the category, you get spaces which are interpretable as convex spaces in that context. So let's analyze a bit more in detail the metric case, which is the one I've been working on the most. There is this very nicely behaved monad on the category of complete metric spaces, and the algebras are what they should be, in the sense that they have to be objects of our category, so complete metric spaces, and have to be convex in some sense. So closed convex subsets of Banach spaces somehow are the convex objects, so to say, in the category of complete metric spaces, and that's exactly what the algebras are. So what are partial evaluations? Partial evaluations are partial averages, and this is very important in probability theory. So here's an idea. You have a probability measure on some space. So what do? You first of all, you break it into pieces. Just like, remember, we had this formal sum and we were summing just parts of it. So here's the same. We have a probability measure. We break it into pieces and then take the average of each piece and replace it with the delta weighted by the amount of mass of that piece, and then put them back together. Now here's an example where we broke this into 3 pieces. It doesn't need to be finite. It could be an infinite family, and then it's way more difficult to draw. Okay, but the idea is you replace something by something that's more concentrated, like locally, so to say. Okay, so the new distribution is going to be more concentrated, or if you want, less random, less risky in some sense. You can prove that for this case you always can compose partial evaluations. So the multiplication square, at least for element, for like single elements, is weakly Cartesian, so you can actually compose partial evaluations. And the relation that you get on PA, on the space of formal expressions, is actually a very well-known construction, sometimes called a Choquet order or a convex order or a risk order even. And it's used even in mathematical finance. Even the economists like Rothschild and Stiglitz were using it to assess how risky some random variables are, at least for the case of the real line. So this is actually used in mathematical finance to say that something is riskier or safer. So I like this because in category theory, often you have a construct which you derive from proof principles, and it turns out that a known construction in a different field is an instance of what you just created or thought you created, and this is the case, surprisingly so, for a concept in mathematical finance. That's the partial evaluation if real numbers are considered as an algebra of the Kantorovich monad. We can say more. In probability theory or in measure theory, there is actually already a notion of things that are like expectations, but only partial, which are conditional expectation. And it turns out that these concepts are the same once you translate them properly. So it turns out that as a corollary to a theorem that's known since the 80s, given probability measures on A, so formal expressions if you want, on PA, then P is a partial evaluation of Q if and only if these two probability measures are laws, are distributions of random variables, which are in relation of conditional expectation. For those of you not familiar with conditional expectation, here's a rough idea. So suppose you have a measure on your space, here is the red one, and the function, here's the blue one, on your space, which is measurable. And suppose you take a coarser sigma algebra, think of a partition, take it, for example, a finite partition. What is a conditional expectation of this function with respect to this new sigma algebra, or this new partition? Is a new function which is constant within the cells of the partition, so which is measurable for the new sigma algebra, but such that for each cells of the new partition, or for each measurable subset of the new sigma algebra, the integral is the same. So the area of these rectangles is the same as the area of these old shapes. Okay? So you're replacing this function in the cell with its average in that cell. Okay? Replace a function with the cell-wise average. That's conditional expectation. Of course, in general, this is not a partition, this is infinite, and it's an actual sigma algebra. But now, why does this correspond to partial evaluations? Well, let's now look at the values that this thing takes. For example, R, so an algebra over monad. So if you have this measure, you can push it forward along this function and get this image measure, like the law of your random variable. If you now replace this function by its conditional expectation, then the image random variable will be more concentrated. Will somehow break your image random variable into pieces and replace them with their average. Okay? So these two things, these two concepts are actually pretty much the same once you translate, once you go from random variables to their distribution. Okay? So that's the theorem in rigor. And some of you may probably know that this allows to talk about martingales. So this tells us that partial evaluations are how you can model martingales in probability using probability monads. I like this because probability monads, until very recently, were mostly used to do measure theory rather than probability theory. Not many people were using probability monads to actually talk about stochastic processes and so on, but mostly to express what measures are categorically. This instead is giving us a way of talk about actual martingales, so things that probability theorists actually work with using monads. Last thing I want to mention, so there is work in progress that we're doing together with the ACT school students. Partial evaluations can be seen as like source and target of a higher dimensional structure, an entire simplicial set, which is called the bar construction. So those are just the tip of the iceberg. If you want the picture, then if you view this witness of partial evaluation from here to here, and this witness of partial evaluation from here to here as two edges of a triangle, then the triple formal expression is like the interior of a triangle, and by removing the mid-level boxes, you get the missing arrow of the triangle. Okay? Turns out that this gives a lot of new compositional structures, similar to categories but much more general, not quasi-categories, they're different. And it's a work in progress that we're doing together with the students of the school of last year, so I hope that I'll be able to tell you more about this in the near future, so stay tuned if you're interested. And for the rest, I think I'll stop here. Let me just say, so give some credit. This is a joint work that I've been doing with Tobias Fritz. I have to thank Slava Matveyev because he's the person that came up with this idea of partially evaluating something. And I want to thank also the students of our ACT school, which are Carmen Constantine, Martin Lundfall, and Brandon Shapiro, with whom we are currently working. All right, so here's some references. If you want to see some details of this construction, of course, you can look at the paper in the proceedings when it's going to go out. It's already in the archive if you want. And if you want to see a little bit more about partial evaluations in probability, you can look at chapter 4 of my PhD thesis, which you can find at this address. All right. Thank you so much for listening, and I hope you found this interesting.